About 3 years ago, my parents and I went on a domestic family trip to a cocoa plantation. There, instead of focusing on the delicious chocolate, I couldn't help but notice these. Massive piles of cocoa pods laid everywhere for visitors to see. Albeit being used as cattle fodder, these cocoa pods still manage to pile up, take up space, thus preventing efficient cultivation. And that brings us to my research today. Good morning, I'm Karina Jane from SMA Citahati Christian School, East Surabaya, and today I'll be presenting about my research called Theobroma Cacao, the Novelty of Biopackagings. So far, Indonesia has successfully adapted practicality, which is needed in every single lifestyle, in means of transportation and storage of items. The most commonly used compound for such tasks is styrene, or more famously known in the form of styrofoam boxes. However, styrofoam itself has negative impacts towards Indonesia's environment, and by thus doing so, has dominated headlines nationally. In fact, about 59% of the waste entering Indonesia's seas are in some form of styrofoam. Once that percentage is converted into nominals, it is estimated that about 350,000 tons of styrofoam waste appear each and every year. On a brighter note, Indonesia is also the third biggest producer of cocoa in the entire world, producing up to 800,000 tons of cocoa beans each and every year. Despite that, it is not commonly known that Indonesia only utilizes up to 23% of the actual fruit, throwing away 75% the cocoa pods, resulting in a massive waste of 2.5 million tons. These cocoa pods are also known to contain 35.4% cellulose. Cellulose alone is a natural polymer, a polysaccharide to be specific, that is fibrous with high tensile strength. And those backgrounds lead on to the research goal today, which is to investigate whether or not these cocoa pods can be used to create a biopackaging material safe for the environment. Moving on to research design, first to set variables, delignified cocoa pods is mixed with ethylene vinyl acetate, or more commonly known with its abbreviation EVA, in 3 different amounts each. Thus, 9 samples are created. The creation of samples begins with cocoa pods being chopped into cubes, soaked in sodium hydroxide 5% for 24 hours before being rinsed with water until pH reaches 7. Later on, cocoa pods are dried and ground before being mixed with EVA at 105 degrees Celsius, and such mixture is pressed between glass. Moving on to research methodology, further testing involves the investigation on samples' tensile strength, elongation at break, calculating its Young modulus value, and also conducting a biodegradability test in which weight loss is calculated after samples are being buried below 45 grams of humus soil for about 1 week. It is important to note that within such observations and investigations, each sample has 3 trials, and the results are analyzed with ANOVA probability 5%. Now, the results obtained were as follows. For tensile strength, the highest value was found within sample D at 0.28 megapascals, while the lowest was found within sample F and sample C at equally 0.09 megapascals. Since tensile strength refers back to the maximum load and maximum stress samples can withstand without being elongated prior to fracture, it can be stated that sample D is able to withstand the greatest amount of load and resist the greatest amount of tension compared to all samples, especially to sample F and C, which can only hold up to the lowest. Continuing on from the graph, it can be stated that increased cocoa pod cellulose content does increase tensile strength values until a maximum point, which can be predetermined as sample D before decreasing even further. However, for increased EVA composition, tensile strength decreases always. Indirectly affected by tensile strength is its Young modulus. The highest Young modulus value was found within sample A at 4 megapascals, while the lowest was found in sample F yet once more at 0.8 megapascals. Such low results in sample F may be attributed due to the combined properties of increased EVA composition and way too much cellulose content. Relating to that, we may see that within the graph, young modulus values increases with increased cocoa pod has cellulose content, while it decreases with increased EVA composition as well. Such results, especially affected by higher cocoa potash cellulose, can be attributed due to the fact that hydroxyl groups within the cellulose chain form hydrogen bonds with oxygen atoms, thus holding chains together. This, of course, increases stiffness, thus increasing tensile strength and Young modulus even further. However, after the optimum point predetermined as sample D, irregular fiber orientation occurs, weakening bonds within the cocoa potash cellulose and EVA matrix, decreasing tensile strength and also its Young modulus. For EVA content, it can be said that higher phenyl acetate composition causes weaker interfacial adhesion with the cellulose fillers, reducing stiffness, thus increasing flexibility, and also decreasing tensile strength and Young modulus. Moving on, we have the results obtained for the elongation at break values. The highest value was found within sample G at 100%, while the lowest was at sample C 16%. Elongation at break measures how much samples can be stretched before it breaks as a percentage of its original length. Thus, elongation at break states the sample's capabilities of undergoing deformation while also stating the ductility of such sample. Therefore, with sample G having the highest elongation at break values, it can be said that sample G has the tendency to deform up to 100% of its original length, while sample C tends to fracture at an increase of 16%. Looking back at the graph, it can be seen that the effects of increased cocoa potash cellulose content decreases elongation at break values, while EVA composition increases it. That again can be explained using the same explanation as before. Cocoa potash cellulose content causes hydroxyl groups within its cellulose chain to hold chains together again once more using hydrogen bonds with oxygen atoms, increasing stiffness. However, contrastingly, after the optimum point, irregular fiber orientation also reduces flexibility, thus showing that increased cocoa potash cellulose content decreases elongation as a whole. However, for EVA, higher phenyl acetate with its large molecular weight causes weaker adhesion bonds to occur with cellulose fillers, reducing stiffness yet increasing flexibility, thus increasing its elongation at break. Lastly, the results of the biodegradability test, its weight loss, are as follows. When such results is placed in a bar graph, you may notice that the highest biodegradability was found within sample C at 22.88%, while the lowest was found equally in sample G and H at 7.32%. This alone shows that with higher cocoa potash cellulose content, and especially with the addition of lower EVA composition, biodegradability is promoted to increase weight loss. This may be explained by the fact that fiber acts as a more organic composition, especially when compared to EVA, for bacterial microbes in the soil to degrade polymers into monomers using enzymes such as cellulase to degrade cellulose. Once we take the best sample, being sample D, we may notice that the properties of tensile strength, Young modulus, elongation at break, and even biodegradability is higher or similar to those biopackagings made from cassava starch and sugarcane baggings. However, it is important to note that sample D is lower in terms of biodegradability compared to cassava starch biopackaging by 9%. Thus, in conclusion, it can be said that cocoa potash may be utilized as a biodegradable packaging material safe for the environment with the addition of EVA at the best ratio composition of 2 to 3, EVA to delignified cocoa potash. In the end, it can be said that chocolate does save everything, even the environment. Thank you.